basic properties of the stars. And yesterday we talked about what is in between stars. So that is basically about interstellar matter, right? So we need to know about interstellar matter because now today's lecture we will discuss about formation of stars. Now, when we talk about formation of stars, it is always important to know about the properties of interstellar matter, like what they are made of and what kind of material that you have in this interstellar matter, those kind of stuff. That's because you will soon understand that it is the interstellar matter that contributes to the formation of the stars under different conditions, right? So that's what will happen. Now, so I have shared my presentation with you and assume that all of you can see it, right? And let me just go into the full screen mode here. Just change the sharing. Right. So I guess right. So I guess all of you can see the presentation. I mean, in the full screen mode, right? There is another screen with me, so that I hope that you are looking at the correct screen. Now, the diagram that you see here basically kind of explain the whole complete story in this stellar formation process, right? So that's why I have this diagram at the beginning. And once you, so what we are doing in this coming, let's say next 4 to 5 lectures, is that we are trying to understand each phase of this diagram. This diagram kind of summarize like probably 6 to 7 lectures that I will be doing in this week and probably in the next week. Now, when you consider about the formation of stars, it is these molecular clouds that we talked yesterday is the place that will help for the birth of a star, right? And from this molecular cloud, under some specific conditions, you will have these protostars created, right? And once you have the protostar, based on certain properties that you have for the protostar, there will be a birth of a star, and the initial mass of that particular star will depend on some properties of the protostar, and based on the mass of that initial star, the evolutionary process also will be different, right? Basically, if it's a very massive star, it will become a supergiant star after some time. So massive star means the stars which they have a mass greater than 8 times the mass of the sun, right? So then you will have a red supergiant, and after that you may have a type 2 supernova explosion. So you may have heard about the supernovas. So it can become a supernova. And after supernova explosion, there can be 2 things that can happen to these stars based on, again, the mass of the star. This particular star could become a black hole or a neutron star, right? So that's what you are seeing here, right? So it could become a neutron star or a black hole depending on the mass of the star, right? On the other hand, when you look at this path right here, if the initial mass of the star is less than 8 times the mass of the sun, again it will become a red giant. Sorry. And after a red giant, this particular star will become like a white dwarf. And then after that, depending on the mass of the star, the white dwarf could accrete some matter from a combined companion star nearby, and depending on the mass limits, this particular star could become a type 1a supernova. And there are two types of supernovas, by the way, we are learning, right? So this is called type 2 supernova that goes with these high mass stars. And there is another one that we called as type 1a supernova that goes with the low mass stars by creating some matter from surrounding stars. And then after the type 1 supernova explosion, uh, this star could become a white dwarf, and there is another path for that as well. Without having a type 1a supernova, you may have a planetary nebula and then a white dwarf as well. And there is a possibility that this will become a black dwarf at the end, right? So these are, and there is another one possibility if the mass is very, very low at the initial stage, the star will not proceed like this, so it will become a brown dwarf, right? Now, in our lecture series, what we will be discussing is, we will discuss this part today, right? And then we will go through what happened, how these protostars will become, and what will happen in this particular stage, and then how it goes to the next stage like that, and then to these high mass stars, which is about supernova and black holes, right? So we are going to discuss a little bit in detail about each of these phases, right? So that's what we will be doing throughout this lecture series about the stellar evolution. And of course, even inside these evolutionary process, there are a lot of things that we could discuss, but we have a very limited time allocated for these lectures. So I will go through basic things, right? So we will not go into very deep and discuss everything. And to start with, so I'm going to start with this particular phase right here about the stellar evolution. Now to start with, this is an image of a Carina nebula, right? Which is taken from the Hubble Space Telescope. Of course, now we have a better image from James Webb as well. And you can see that this image has the jet streams like here and here. You can see these edges that you have this jet stream kind of things right here. So these are actually powered by newly forming stars, right? Embedded inside gas and dust. Now, what actually has happened is part of the clouds that you see here are glowing from the energy that these very young stars are emitting, right? So they get this energy from the young stars, and then you have these jet streams, right? So this picture will tell you that these formation of young stars normally happens around these gas clouds, right? So we have discussed that in the last lecture as well. What we need to discuss here is what is the relationship between these formation of stars and these gas clouds, right? So there should be certain conditions that need to satisfy in order to form a star from this interstellar matter. So the gas clouds are inside this interstellar matter, right? Now, so the question is, what triggers this star formation? Actually, what should happen, or the produce a condition that is suitable for the formation of stars, is that this interstellar matter has to be compressed to a very high density. So that should be the basic requirement, right? So there are several ways that this might occur. So the condition is, once again, this interstellar matter should be compressed into a very high density, and you can have this in a few different ways. This can occur. So the one way is a shock wave from an exploding star, right? So then, which can cause instabilities and collapse in giant molecular clouds, right?
Now, these shock waves can come from actually supernova explosions. Now, I know that we have not discussed about what is a supernova. So just let's keep it in this way. Supernova uh, is kind of an exploding star, right? So when you have these exploding stars, they uh, send out shock waves from the star. Now, these shock waves can cause different instabilities in the interstellar matter, right? Because everything is in this interstellar matter now. Uh, Now, these instabilities in interstellar matter can lead to collapses in these giant molecular clouds. And once you have these collapses, those regions could lead into formation of new stars. Right? So that is one thing that can happen. And the same effect can have from the radiation of hot young stars. Right? So this is why the places like this we normally consider as like stellar nurseries, places that will lead to birth of young stars, because you have some young stars there, they will emit radiation. And from these radiations, you will again have instabilities in the molecular clouds, which will lead to formation of new stars, right? And also the third way is collision of clouds of interstellar matter may cause instabilities and collapse within the clouds. So there, it is this condition. I mean, you may have collisions between these molecular clouds, which can also lead to different instabilities. However, the primary condition is if there is any method that you could make different instabilities in these molecular clouds, which will lead to increase in densities in certain regions, that will trigger a formation of a new generation of stars, right? Now, the next question is how can a cloud of interstellar matter become dense enough to form stars? So, how do we know whether this is dense enough or not? We have discussed now, like condition. Condition means you have to increase the density of the molecular clouds in certain regions in order to have the stars formed, right? Now, actually, this formation of a star is a battle between gravity and pressure, right? So what happens is when you have these gas clouds, uh, they are attracted to each other via all the particles in a gas cloud. So they have a certain mass, so they are attracted basically due to the force of gravity. So the gravity is the attractive force, no? So what happens is they attract close to each other, they more and more attract to each other and close together, right? So what will happen is this will lead to an increase in the pull of gravity again and again, because when particles get much closer and closer, the gravity also keep increasing, right? So this will lead to increasing density and then gravitational collapse of the clouds of interstellar matter. And then you will have a gravitational collapse. So which means everything will be collapsed to one region, right? Now, when this process happens, this is obvious now. When things are get closer and closer, the gravity increases. So they will get even more close, right? And there is another process that will happen to counterattack this gravitational effect. So that is the pressure due to the motion of particles within the clouds of interstellar matter. So when the things get closer and closer, what will happen is this will build up an internal pressure, right? Now, once you have an internal pressure, that pressure will pull all the particles towards the outward direction. So that process is completely opposite side of the gravitational effect, right? So what will happen is this due to this pressure, uh, the pressure can slow down this gravitational collapse, right? So I think I hope that you can understand this. So if I let me draw this, this is like, let's say you have a gravitational cloud like this because of the gravity. So everything will pull towards the central region. So what will happen is once everything is pulled toward the central region, this molecular cloud will become, more and more condensed. But at the same time, there will be a pressure build up at the central region when things get closer and closer. And once the pressure builds up, this pressure will create a force towards the outward direction. Right? So that's why I told you this will be a battle between gravity and pressure. Right? So I hope now you could understand it. And now what will happen is when you have these instabilities within these giant molecular clouds, there will be some regions that are sufficiently cold and dense for gravity to win out over pressure. So you have this uh, battle between gravity and pressure, but there may be some regions that are cold enough to gravity to win this battle over the pressure, right? So when that happens, each of these regions will become eventually a star, right? So that's how you have protostars. So there will be regions that are cold enough that the pressure cannot, overcome the gravity. When that happens, the gravity wins. So when that happens, those regions will become a star. Right? So I hope you can understand it in the most simple way, right? So basically, it's a story or a battle with gravity and pressure. Now, basically, when you take one of these giant molecular cloud, this cloud may contain hundreds or thousands of these dense cold regions, right? So initially, each region is cold and thousands of times larger than our solar system, right? So this you can have large number of cold regions in this one molecular cloud, which will lead to create large number of stars, right? So what will happen is each of these regions, these cold regions will gradually shrink to the size of our solar system with central temperature about 10,000 Kelvin. So what will happen is these cold regions, so they do not have much support from the pressure, and because of that, the gravity will continue to collapse those regions. And once you collapse it, even though it is cold, the temperature will increase, right? So this temperature can go up to 10,000 Kelvin. And while this is happening, they will shrink to size of our solar system, right? Now, each of these objects is called a protostar. Now, this initial stage of a star that that is created during this process is what we called as the protostar. Now, if you remember the first diagram that I showed you, the protostar is the first kind of a star before everything else, right? Right. Now, if you look at little bit about the physics behind this formation of stars, so there is a theorem called Virial theorem, which describes the conditions for the equilibrium for a gravitationally bound system. So that is this Virial theorem. I am not aware whether you have learned about it or not. So if you have done some classical mechanics, you may have learned the Virial theorem. But my attention here is not to teach you about the Virial theorem, but just to give you the conditions that is imposed by the Virial theorem and use that to show you a certain condition that we can derive in order to have a star, right? Now, what according to the Virial, when if you take the Virial theorem, we normally denote K as the total kinetic energy of a molecular cloud in this particular case, and then the U as the gravitational potential energy. And once you have these two types of energy, you can say that if 2 times the kinetic energy greater than the magnitude of the potential energy, gas pressure will dominate over gravity, right? And if the other case is if the 2 times of the kinetic energy less than the gravitational potential energy, then gravity dominates, right? So it's obvious now the kinetic energy usually comes due to the pressure, and the U is the gravitational energy, potential energy, which is basically due to the gravity. Now, if the kinetic energy, 2 times the kinetic energy is lesser and the gravitational potential energy is larger, the gravity dominates, right? This is the condition where you can have a star, right? So you can use this condition to derive a relationship that gives you a minimum mass that we should have for a particular molecular cloud in order to form a photostar, right? So I'm going to give you that as an exercise for you just to try, because the condition is given here. So all you need to find is the kinetic energy and potential energy and plug the values here. So here is the question. Assuming a spherical cloud, so the shape of the cloud is spherical, so that you can assume it as a sphere with the constant density. So you will have a density as a constant as well, and the gravitational potential energy for this kind of cloud can be given as U equal minus 3/5 GMC squared over RC, where MC and RC are the mass and the radius of the gas cloud. And the cloud's internal kinetic energy is given as K equal 3/2 times NKT, right? Where N is the total number of particles given by capital N equal MC over mu MH, where mu is the mean molecular weight. And I'm asking find the condition for the collapse, right? I think everything is given here. So you need to find the condition for the collapse. Now, if you do a proper calculation and also find the minimum mass necessary to initiate this spontaneous collapse of the cloud, right? Now, the initial mass density is assumed to be a constant and given by RC equal 3 MC over 4 rho 0 to the power 1/3. Now, I have given you the mass density relation here as well. And you need to find this value right here, value mj. So this has a specific name, and this name is called Jeans mass. And if you plug these values properly to this particular condition right here, 2k less than u, so you are given the value of k, that is 3/2 nkt, and n is given here as well, mc over mu mh. So all you need to do is, I guess if I just show you, so this is like, so you have 2k less than u, right? So your k is given, k is this nkt, so you can plug it here, and while you plug it, so there is a value for n, which is the total number. That total number is given here, so you can directly plug that value here. So you will get an expression, and the u is given from this expression, and you just need to take the magnitude and put it here, and this will give you a relationship, right? So I just want you to try that and see whether you can get this equation right here. So you will get something mc, right? Not mj, should be greater than some value, right? And this particular value where you have is what we called as the Jeans mass at the end, right? So this condition basically known as the Jeans criteria, and the minimum mass is known as the Jeans mass, right? So you have to use this particular relation once again, and then derive this value right here. So as you can see, all the expressions are pretty much visible here. So you should not have any problems of deriving this. So I would highly recommend that you do this yourself and see whether you can get this answer, right? So I have not mentioned the step-by-step calculations, but this should not be a harder one to do, right? So you should expect this kind of, I will expect that you can do yourself these kind of things. Right, so this is called in Jeans criteria to have a protostar. So this is the criteria in terms of physics in order to create a protostar, right? Right, now assume that we create a protostar. Right, so before we go into that, let me give you like 2 or 3 minutes. Can you please try yourself to have this equation obtained? Maybe you can do it yourself, right? So it probably will take time other than that. So let's go into this next section.
about the pre-main sequence star. Right, before we move into the next section, so anybody have any questions up to here? Any type of questions? By the way, can one of you please let me know whether you have like final exams already scheduled for this semester or not? Because I heard it maybe next month. I don't know. Does anybody have any idea, or you are informed whether when is your final exams or not? Because I need to finish the lectures before that. And right, so it's in the second week of September. So which means we have time, right? So I don't want to rush it if you have too much time then. So I will, which means so I thought it's in the August. So if it is in the September, then it should be okay, right? And just to let you know, remind again, so you will have this whatever call in-class examination at some point. So I am planning to do it in the next week at some point. But that will be decided by your department once I send them the paper. So I didn't still. So by once I send it off, and I will probably update you, and we'll ask the head of the department to let you know a date for that. Right. Right. So yeah, thank you for that information. So if it is in the second week of the September, then if that is the case, then you will have time. And the other thing is, I think I have posted the set of problems for you to work out yourself, and these problems are based on what you have done up to now. And most of the things are based on the first 10 to 12 maybe things that we did up to the stars. And also some information will be some needed from the properties of the stars as well. So try those set of problems. And I have actually shared it from my previous class last year, because there is nothing difference about these problems. So if you cannot access it, then please let me know, right? So I will repost it. Right. If you do not have any questions, let me go into this next phase. So one of you asking whether this in-course exam will held as an online exam. I think I don't think so. So what I was requested is you online the university, and because of that, uh, uh, you will have it in your department, I guess, right? So I just will be sending the paper, and they will hold the exam. That's my understanding based on the discussion with your dean and the head of the department at the early in the month. I don't know whether the conditions have changed. Are you still in the? I guess all of you are in the university, right? So if you are at home, that may be different. So does that mean that all of you, your university, is that your university is closed these days then? Oh, okay. So I didn't know about it. So I will just check with them, the department. Oh, right, 1st of August. So that makes sense. So I didn't know about it. Sorry about it. So then I guess you will have it in after 1st of August. So I will just check with your department and update you about that condition, right? And also, if that is the case, we actually do not need to rush these lectures as well. I personally don't like it as well. I thought that you have the exams, final exams in the next month as well. So it seems to be not the case, because we are almost done with like 19 lectures. So there are only 10 lectures to go. So we can do it slowly then, right? Right. So thank you for that information. So I will check again with your department and see how it works, right? And
Problem sheet is uploaded as a PDF, and what I am not sure is because I was trying to save the disk space and I reshared the same problem sheet that I used the previous time. What I am not sure is whether you have the access for that. But if you do not have the access, I will post it as a PDF, right? And I highly recommend all of you to go through those problems and try it yourself, right? I may be doing it in one of these sessions, online sessions, or maybe, okay, so you can't access it. So I will, after the class, I will repost it as a fresh PDF. Thank you for that update, right? So the other thing is make sure that you do it yourself. I may be doing it with you in an online session. Now I will just take the questions from you if you have, by posting a recorded video for you how to do it, right? So that can also happen. So that can go in both ways, right? And the other thing is, actually, I was one thing I was trying to do with you is just without having doing these lectures, provide recorded lectures for you and take questions that you have within the lecture period. I mean, this is actually the better way of teaching rather than delivering everything. But the problem is that it seems that all of you are not joining with the lectures. What I feel is only 1/3 of the class is here, and also, I mean, you sometimes may have different issues in asking questions and those kind of things. Other than that, that would be the better way of doing it, which I plan to, do it here as well. Right. So let's come back to the lectures again with all this information. Now, what we have discussed up to now is what would happen to how a protostar is created out of the interstellar matter, right? So last week we talked about interstellar matter, and now today we are talking about what is the physics behind triggering star formation. That is this genes criteria, and at the same time, so from the genes criteria, if the genes criteria is satisfied, we will have a protostar at the end from this whole region of these large molecular clouds. So once we have a protostar, then we need to discuss what will happen as the next step, right? Now, basically, when you have a protostar, the protostar and its surrounding cloud of interstellar matter undergo a continued collapse. So what will happen is it will not stop like that. Then now you have a protostar, but the interstellar matter around that will continue to collapse. Now this collapse will be occurring faster in the inner regions. And what will happen is the protostar will continuously increase its density and will become hot, right? The temperature will also increase because the matter will fall down to it now. So when matter will fall down, the density will increase and the temperature of the star will also rise, right? And eventually what would happen is the protostar begins to radiate mostly at IR infrared wavelengths. And the protostar cannot be seen at visible wavelengths since its light is absorbed by dust in its surroundings. Now, these protostars, you don't expect that you will see a protostar when you go outside and look at the sky, right? So that's not going to happen because the protostars, even though it begins to radiate mostly in the IR region, not in the visible region, at visible wavelengths, you cannot see protostars, right? Because these visible lights will be absorbed by the dust around the star, right? What will happen is, as a result of this radiation that's going outward from the protostar, at a certain point, because the radiation, there is something called radiation pressure due to this radiation, right? And because of the radiation that's going outward, at a certain point, there will be a bottleneck. Bottleneck means there will be, sorry, not probably that is not the best word. There will be a limit for this accretion of more matter from the interstellar matter. So it will stop at certain point, right? Now, when that happens, we used to tell that the protostar is now called a pre-main sequence star, right? So these are specific names that you are probably listening for the first time. Because of that, make sure that you remember these names, right? A protostar, then pre-main sequence star, right? So when I say tell about protostar, you should have in your you should have a picture in your mind what that means, right? So you have a protostar. So the protostar continues to radiate, uh, do the continues to radiate, and once this it radiates actually in the IR wavelength, so you cannot see anything because of the surrounding molecular uh, clouds and also the dust. And at a certain point, because of this radiation, the accreting matter will stop at a certain time, right? Because of the outward radiation. So when that happens, we used to tell or call this protostar as a pre-main sequence star, right? So that means the star is ready to go into the main sequence of the HR diagram. And if you remember that I have briefly discussed about the HR diagram previously, right? So I'm going to, so this is just an example of another star forming region. Now let's see the evolution into the main sequence. Now our star is now in the pre-main sequence stage. Now let's see how it move on to the main sequence stage, right? So what happens is now you do not have materials, coming from the interstellar matter. However, these pre-main sequence stars continues to heat up and gradually shrink in size. So that is basically due to the fact that you have more material that's coming towards the you have the central region of the star, and all these materials uh, in the pre-main sequence star is they have a certain mass, so they are still attracting gravitationally towards the central region, right? So because of that, uh, the star continues to heat up from the central region, and it's also shrink in size. That's because of the gravity, right? So the what will happen is normally the star will continue to collapse towards the central region. When that happens, the central temperature also will increase, will keep increasing, right? So that is basically what will happen in any object, right? And at a certain point, this the temperature of the core, so that means the central region of the will reach to 10 million Kelvin, right? And so when this happens, the hydrogen in the core now ignites. So that will happen if you have learned about these nuclear reactions or the fusion reactions. And you know that at the central region of the star, it is mostly hydrogen that we have, because this is a part of interstellar matter, and all the materials have come from the interstellar matter. And we have learned that 90% of the material in interstellar matter is hydrogen, right? So now you should have hydrogen inside these pre-main sequence stars, right? In the central region, you have hydrogen, and because of the gravity, everything keep collapsing, and which will increase the central temperature gradually. And once this temperature reaches to a point where it is 10 million Kelvin, then the environment is correct for these fusion reactions for the hydrogen, right? So if you have learned about some nuclear fusion reactions or nuclear physics, you know that when you have this kind of higher temperature, so that is the required temperature for hydrogen fusion. Now you have 90% of the hydrogen in the core, so you have the correct temperature now. Because of that, there will be a thermonuclear fusion, which will turn hydrogen into helium, right? Now, when this happens, all of you know that when hydrogen fused and converted into helium through a thermonuclear fusion like this, there will be a huge amount of energy released due to this process. You know how violent and what kind of energy released from nuclear reactions, right? So this is a nuclear reaction, a fusion reaction. So there will be a huge amount of energy released due to this reaction. And as a result of that, the energy gives off as radiation. And this is the event that signifies as the birth of a star, right? Now, if you actually compare this with, so I would like to compare this with the birth of a child. So it's, the child so it will take around, for the birth of a child, once it is created under certain conditions, it will take around 10 months, right? That the child will grow into different stages and the birth will happen at certain stages after 10 months, right? So this is something similar. So all the conditions that we have talked up now is like a development of a child. The only difference here is the conditions are different for a star, and the amount of time it takes to go into different stages will be very long, right? So you will have a childbirth within 10 months, but that is not going to happen for stars, right? The process is different and the time period is huge. So otherwise, other than that, it looks like the same, right? And this signified the birth of a star. And then we used to tell that the star finally arrives onto the main sequence, right? Right. Now this is the HR diagram, which I probably have talked before. And I can actually summarize everything that I have told you using this particular diagram. That is, if you look at, once again, if somebody missed these HR diagrams, HR diagram is called Hertzsprung-Russell diagram, and that is very widely used in astronomy to explain this evolutionary process of the stars. And as students who have done astronomy, you must have a very good understanding of HR diagrams, and you cannot talk anything about stars without an HR diagram, right? I mean, you need to know about it. Now, what this, So what this particular diagram tries to explain you is, in this x-axis, you are given the temperature. Only thing that you need to be careful here is temperature is increasing towards this direction. It's kind of a little bit weird, right? And then the luminosity is increasing this direction, and sometimes people use the magnitude as well to denote the luminosity. You denote in terms of magnitudes, you will see magnitudes are decreasing towards this direction, right? So that's because lower the magnitude, brighter the object, right? So that is the reason for that. And what I have mentioned here is, in an HR diagram, there are specific regions that we can talk. What is important for us here is the main sequence. So this red line right here is what we called as the main sequence. And then you can see that there are certain black lines drawn towards the main sequence at different stages. And you have different numbers that are given. So what you need to identify here is, in the main sequence, so I have basically explained how do we have a main sequence star at the end, right? This, after protostar, you have a pre-main sequence star. Now the pre-main sequence stars are somewhere here, and then they will take some time to enter into the main sequence. When it enters the main sequence, they will be burned hydrogen into helium. So that's what will happen most of their lives, but you have to start that process, right? From the pre-main sequence stars, once the temperature is correct, they will start this fusion reactions. Now, in order for that to happen, different stars take different times, right? And if a star has a considerable amount of mass like that, for example, a 15 solar mass, then those stars will move on to this top
left part of the main sequence. Basically, what that means is these stars will have a higher temperature and a higher luminosity. So they will be bright stars when they are in the main sequence. And you can see that. So if the star has a 9 solar mass, then they will go to little bit lower side of the main sequence. So they will be still bright, but not as bright as these high mass stars, right? Like that, you can see that when the mass decreases, they will go into lower level of this main sequence in the chart diagram. So what that means is if it goes to the lower level, that means that their mass is less. So you can see that these stars are 0.05 solar masses. Remember, the symbol denote the solar mass, right? So those stars will go into lower level because of their mass is smaller. So they do not have much material to burn up and create these huge brightness values. And their temperatures is smaller as well. And there is another thing to understand here. When you have the number of years it takes to enter the main sequence, right? You can see that these huge high mass stars, they will take around 10 to the power 4 years uh, to enter into the main sequence. So that's what this number tells you. It is 10 to the power 5 years when you go into this little bit lower mass stage. But if the mass is really low like this, around 0.5 solar mass or so, so then it would take around, more than 10 to the power 7 years to enter into the main sequence, right? Now you can understand a very prominent feature here for all the stars. If the mass is higher, their brightness will be higher, their temperature will be higher, and at the same time, they will quickly go through this process and enter into the main sequence. For the low mass stars, their their brightness will be lower and their temperature will be lower at the end when they enter into the main sequence. So that means they are in the state of burning hydrogen into helium. At the same time, even though these stars are low mass stars, they take a longer time to enter into the main sequence, right? So those are the prominent features that you can understand. And you should now understand why I have told you that why this HR diagram is important, because you can discuss almost all the properties of stars using this one single diagram, right? So we will continue to take this HR diagram and again to discuss and relate different properties. Now, as you see, even from the last HR diagram, uh, the amount of mass in a collapsing fragment of interstellar matter actually decides the star's eventual mass, right? And also that also determines how long it takes for the star to form. So that's what I have mentioned by looking at that HR diagram also. Now, for example, if you take a star like a sun, uh, it takes about 50 million years to form, right? Now, the most massive stars form in about 1 million years, right? So the least massive stars may take more than 1 billion years, right? Like that. So it's the smaller the mass of this proto star or the pre-main sequence star, it takes longer time to form. To form means enter into the main sequence by burning to start this process of burning hydrogen into helium to nuclear fusion reactions, right? And you should understand this why, because when the mass is smaller, you can see that the gravitational effects will become smaller, so it will take time for those stars to um, shrink in size and then increase the central temperature to fuse hydrogen into helium. So that should be the reason, right? For the more massive stars, you have a lot of
mass inside that. So they will quickly collapse gravitationally towards the central region, which will increase the central temperature faster compared to these low mass stars. And that will lead to start fusing hydrogen into helium quickly, right? Or sooner. So that is why their lifespan has become shorter, right? And so these are the things actually we discussed from this previous slide, right? About from the HR diagram, you can explain all these things. Now, a good way of deciding that you have a good idea about this stellar evolutionary process is that whether you can check whether you can completely understand these HR diagrams or not. If you can understand and explain everything from the HR diagram, that means you have a good understanding about this process of formation of stars, right? And also the other thing is the mass of a star also determines its main sequence luminosity and the surface temperature. So that's what I have explained here. If it is lower in the mass, if it is a low mass star, its temperature is smaller and the luminosity is also smaller compared to high mass stars, right? So that's why I told you from the HR diagram, you can explain everything. And also it will have these properties most of its life because there are other stages now. Right, now the next thing is there are certain stars or some fragment of interstellar matter, actually they are not massive enough to turn into stars. However, there will be protostars, right? So they will create a protostars, but this initial mass is not enough to convert them into real stars. The real stars means the stars that will move on to the main sequence eventually, right? Because the reason is actually these protostars are unable to generate central temperatures that are hot enough to burn hydrogen. Remember that I have discussed, you need to have a certain temperature to burn hydrogen into helium. So that you have learned from nuclear reactions, right? So that should be around at least 10,000 Kelvin in the central region. But in order to achieve this 10,000 Kelvin range for the temperature, the star should have a certain mass that it can collapse towards the central region and increase the temperature itself, right? But there are certain type of stars that has become protostars, but they are unable to generate these central temperatures hot enough to burn hydrogen. And this is basically due to their mass is not enough to do this, right? Basically, statistically, this happens for all the protostars which has masses less than 8% of the mass of the sun, right? So if a protostar has a mass that is less than 8% of the mass of the sun, these type of stars are not capable of creating that central temperature to burn hydrogen into helium, right? Now we used to tell for these kind of stars a specific name, that is brown dwarfs. Now if you heard in the news or anywhere that probably scientists have discovered a new brown dwarf, then you should have this idea about what is a brown dwarf and how it is created and why we have these brown dwarfs and why it is in the news as well, because the brown dwarfs are stars that has less amount of energy. They do not have much energy to shine themselves because there are no nuclear fusion reactions inside brown dwarfs. And because of that, they are not easy to find, right? Because they are not bright. So you have specific instruments to search for brown dwarfs, right? And also we used to tell that these stars as failed stars because these stars are failed at some point to continue in their life cycle, right? So these are called brown dwarfs. Brown dwarfs give off some light as they gradually cool, but they are much fainter than normal stars, and that is why it's very hard to detect this brown dwarf. Now, the first confirmed detection of the brown dwarf took place in 1995. So you can see that it's not much long ago. It's around like 25 to 30 years ago that the astronomers have confirmed the detection of first ever brown dwarf, even though it was theoretically predicted earlier. So that is basically due to the fact that brown dwarfs are hard to find. And the other factor is This is an example of detecting a brown dwarf star. Other factor is actually, these are actually some of the brown dwarfs and the sizes and the surface temperature of brown dwarfs, different brown dwarfs now we have found. You can see that this is in comparison with the sun. Sun is the most huge object, and also you can see there is the planet Jupiter is here. Now you should straight away see an issue here. The sun and the sun is okay, but the sum of these brown dwarfs like T1, Gliese 229b, so these are comparably very pretty much similar to these planets, right? So because of that, then you have to think about differentiating brown dwarfs from planets as well, right? So that's why you have to consider specifically about the low mass brown dwarfs and high mass planets. Now, when you look at the brown dwarfs, there are some brown dwarfs, they are about the same radius as the Jupiter, as you saw, regardless of their mass. So the brown dwarfs normally, this covers the mass range of about 13 to 80 times of the mass of Jupiter, right? So their size is the same, but the mass range is huge, right? Now the problem is this makes it harder to distinguish low mass brown dwarfs from high mass planets because they kind of have the same size. And because of that, International Astronomical Union considered the deuterium fusion to differentiate between brown dwarfs and the planets. And what that means is if an object has an enough mass to fuse deuterium, so that mass is around 13 Jupiter masses, so 0.012 solar masses, it is called a brown dwarf. Once again, if you have an object that is enough mass to fuse deuterium, it is called as a brown dwarf. Object with less than 13 Jupiter mass do not fuse deuterium and are usually considered as planets, right? So that's how you differentiate these low mass brown dwarfs and high mass planets, right? So that's an extra detail, right? So this actually completes today's lecture, which is about basically about the first phase of the stellar evolution. So that means stop sharing. So that's basically means the first part, that is what triggers the stellar evolution, right? What triggers the star formation from interstellar matter, and also how a protostar is created and how a protostar can become a main sequence star. So we discussed that part, and that's basically if you look at that first stellar life cycle, you will understand we have basically discussed about that first column, birth of a star. And we now know that our stars are on the main sequence of the HR diagram. And on the next next lecture, we can discuss actually about what happens in the main sequence. Actually, we have one possibility is already discussed, that is about the brown dwarfs. Now, in the next set of lectures, we will take to discuss some of the properties of the stars, and also separately what happened to these massive stars and the low mass stars. And actually, this lecture series will answer some of your questions you may have if you are enthusiastic about astronomy, that like what is a neutron star, what is a black hole, those kind of stuff, right? So those everything will come in at some point in this evolutionary stages, so that we will clearly understand how a black hole is created and what is a neutron star and what's a supernova explosion. All these are actually inside this evolutionary life cycle at in different stages, right? Right. So anybody have any questions?
Okay, there is another question asking in this course whether this exam will be a MCQ or a question paper. For the in-class examination, you will have an MCQ paper, but for the final exam, you will have two parts. Generally, there will be a question paper with MCQs, around 15 questions or so. And then there will be a separate question paper that you have. As far as I remember, there will be 3 questions that you have to answer to. I will actually post that last year's question paper for the Google Classroom as well for you to look at. But just to keep in mind, I have a habit of changing the lectures. I usually do not like my contents, like from 1 year to the next year, usually not exactly similar, but they are somewhat, mostly they are similar in if there is no special reason to change, but there will be some contents that I will use to newly add to the lectures. For example, you have done about the sun separately in this time, which I haven't done in the last year. Like that, there will be some changes which will be incorporated into lectures and your exams as well. However, I will post there will be 2 past papers. Just to let you know, your syllabus has changed a bit, I guess, from the last year, and because of that, your paper, I made my slide change because in previous years you did not, I mean, before 2019, I guess you did not have a MCQ paper. What you had was like a structured question paper that you have four questions as far as I remember, and you need to complete 3 out of those 4 questions. But now it has changed. As far as I remember, it's a MCQ paper that all of you have to answer. It's a compulsory one, which consists around 15 to 20 questions. Plus, then you have a structured paper that you have to answer these questions. That means around 3, there will be 3 questions that you have to answer 2 out of that. So that was kind of the structure of the paper from the last year. Yeah, so it should be somewhat, more or less close to the same structure. So I hope that probably answer most of your questions. Right. I mean, this is a course that, I mean, you should like it. I mean, that's how it works, right? I do not have any plan to make a very hard exam that you cannot answer or not. The idea is, what I expect from you is, once I teach the content, I expect as a student who did astronomy, you should have a kind of a knowledge to deal with, answer these fundamental questions in astronomy and one step above, right? So that means a little bit in detail about these evolutionary processes and those kind of things, right? Right. So any questions? The other thing is, actually I used to give some exercises for you as well in the previous lectures to observe the sky and those kind of things. But this, the astronomy is a science that I mean, that is attached to the sky, but at the same time you need to consider about the weather conditions as well. So from my experience, I know that like the month of May, June, July is not the best time to observe the sky. So if it happened to get late, I may ask you to do an observation session in the next section, but these are actually up to you to do, I mean, at this time, because I didn't assign it at the first place. So you will, I'm not going to give you any marks, but if I assign something for you to do, like a sky observation, something that students who are doing it really will get an advantage in an exam, because I used to ask some practical things based on those as well. I mean, if I assign that, right? So I haven't still. Any other general questions like that? I mean, feel free to ask anything. Right. So if you do not have any questions, actually I plan to have the next lecture tomorrow, but I'm not quite sure with the time since I'm. So I will let you